Okay. Edward, you are here. I see your name. Okay. All right. So this is section 7.4 plus 7.5. So we're gonna continue the normal distribution. Actually, the goal of the next sections is to see, we're gonna see why this normal distribution is so important. Okay, it's why it's it's one of the most important distribution. So in this section 7.4 plus 7.5, we're gonna discuss the central limit theorem. So this is about the central limit theorem. All right. So I'm gonna explain the problem here, the problem in this section with an example, and you'll see how this central limit theorem works. Okay. So I'm gonna go with an example. So of course, here, so I'm gonna take a numerical example first. Example, all right. And so let's say in this example, the variable x, you have some variable x. So this x, let's say, represents the length of a single fish taken at random. Okay, this is the length. This variable x represents the length of a single fish, So the word single here is kind of important. Okay, just one fish, so a single fish. Okay, in I don't know, in inches or wherever units. So of a single fish, and taken at random, of course, random fish taken at random, and then we're gonna suppose, of course, that x, let's say x follows a normal distribution. So it's a normally distributed, follows a normal distribution with, let's say, we know the mean, the population mean, or the population average. So the mean. So this is a population mean, right? So this is the average of all. This is a population mean, mu. So mu is equal to let's say 12 or 10.2 inches. Okay. So what I'm saying here, so this is a population mean, which means that, so if you take all the fish, let's say in the lake, you take all the fish, right? And then you take the average length, then that will be 10.2 inches, right? This is the population mean. So this is the mean of all the fish in the lake, let's say, okay? And so we have the mean and standard population standard deviation, sigma. So standard deviation, sigma equals to let's say 1.4 inches. So let's see, 1.4 inches, right? So let's say you want to find the probability that a single fish taken at random, that a single fish taken at random, of course, a random fish, is its length is between, let's say, its length is between 8 to let's say 12 inches long. So it's between 8 to 12 inches long. So again, your x, that's x, the variable x, that's the length of a single fish, right? And you want to find the probability that, so you select a random, you take a random fish, and you want to find the probability that the single fish is between 8 to 12 inches long, right? So you want to, your x, you want to find the probability, right? Capital P of x, that's the length of a single fish, is actually between 8 to 12, right? Between 8 to 12. All right, so this is x between 8 and 12, right? So what will be this probability, right? This is the question here. So we discussed this, of course, in the previous section, right? The section 7.3. And we said, so what we are supposed to do in this case is, any guess, guys? So what will be the, so what we are supposed to do here to find this probability that x is between 8 and 12? So yeah, so what we said, like in the last section, we need to convert, you know, x to z, to the variable of the standard, the standard normal distribution, right? And then we can use our, you know, the table, this chart from the formula sheet, right? So what we are supposed to do here, so using, so section, so this is, so recall section, what we said in the previous section 7.3. So we said first step, we are supposed to convert, you know, x to z, and then we are supposed to use our chart or table 3 from the formula sheet, right? We have the population mean, the average length, right, which is 10.2 inches, and we have our sigma standard deviation, right? So I'm gonna just remind you, the formula would be, so to convert, you know, x to z, we use the following formula, right? So z is equal to x minus mu over sigma, right? Anyway, so like in this example, so we need to find the probability that x is between 8 and 12. So as a first step, so step 1, so we said we need to convert this x to z, the variable of the standard normal distribution. And then we need to convert those values of x. So this, the 8, that's a value of x, and the same for 12. So we need to convert the values of x to values of z. So this 8 converted to a value of z. So we need to use this formula, right here. So it's x, value of x is 8, minus mu, minus the mean, which is, where is it? Right here, the 10.2, right? So it's 8 minus 10.2 over sigma, the standard deviation, right? Which is 1.4. So over 1.4. And then z, so we have z, and then 12, that's the value of x, and you know, we subtract the mean, population mean over standard deviation, which is 1.4. So this will be equal to, of course, so you subtract like 8 minus 10.2, so that will be negative, right? Negative 2.4. Negative 2.4. Sorry.
But it was 2.2.
2.2, sorry, yeah, sorry.
2.2
I was,
divided
yeah.
by 1.4.
Yeah, 1.4. Yeah, thank you, Annie.
And it's negative 1.57.
Yeah,
Negative.
57.
Yeah.
And the other side, so we have this 12 minus 10.2, so that's 1.8 over 1.4. So that will be equal to, so as Anina said, so that will be negative, so 2.2 over 1.4. So that's negative 1.57 Z. And then 1.4 over 1. Sorry, 1.8 over 1.4. That's 1.29. Right. Now, once you convert your x values of x to z, then we can use our chart. We are supposed to use our chart. So here we are supposed to move to the step number 2. But then, of course, here, remember, guys, what we said about the chart or the table 3. So the table 3 gives us the areas to the left, or when the probability when z is less than the number. But this is not z less than a number. So this is not area to the left. This is a z between two numbers, right? This is z between negative 1.57 and 1.29. So in this case, we said what we need to do is to take the difference between the areas to the left of the two numbers. So that's probability that z is less than. We start with the second number, which is 1.29, right? Minus probability that z is less than the other number, the first one, negative 1.57. And now, this difference is in terms of the areas to the left, right? This is the area to the left of, so this is area to the left of 1.29. And this is like the area to the left of negative 1.57, right? So I express this z between two numbers as difference between areas to the left. So now I can use my my chart or table 3. So we have like 1.29. So nearest 10th would be 1.2, right? The 10th position is the first digit after the decimal point, so 1.2, and the nearest hundredth is the 9 here, so that will be 0.09. So like for 1.29, so if you go to the chart, table 3, right here, so it's a positive 1.2, that's the nearest hundredth, nearest 10th, sorry. So you go positive to positive z, 1.2 positive z, right? So as you can see, next to 1.2, there is 0.8849, etc. And then we need to take the one which corresponds to the nearest hundredth, which is 0.9, right? So then the answer, like here, would be 0.9015. Okay, so that's in the row of 1.2, and it corresponds to the hundredth 0.09. So it's a 9015, right? So we need to. So this would be 0.9015 minus. Do the same thing with the, well, this is negative, right? Just be careful because we have negative. So that's negative 1.5, and that's the nearest 10th, and then nearest hundredth would be 0.07. So the answer from the table should be 0.05, I think, 82, right? And so the difference is actually 8,433, right? So multiply by 100. Want to convert this into percentage and multiply by 100. So that's 84.33%. Right? So yeah, so what we are saying, guys, is that so in other words, so the probability that the single fish taken at random is between 8 and 12 inches long is actually 84.33%. So again, this is the length of a single fish, right? Remember, x, that's the length of a single fish. Plus 1. A single fish. All right, now, okay, now let's say we have the following question. So we have a different question. All right, so now B. Let's say you want to find the probability that the mean length of 5 fish. So the mean, so this is the sample mean. Sample mean length X bar of 5 fish. Right, so we have a sample of 5 fish, right? We take a sample of 5 fish, right? And so if I have 5 fish, of course, I can measure the length mean of the 5 fish, right? So the question is, find the probability that the sample mean length X bar of 5 fish taken at random, of course, is between 8 and 12 inches long. Okay, so this question is very different from the previous one, right? So in the previous one, we took just a single fish at random, right? It says find the probability that a single fish taken at random, right? Just one fish is between 8 to 12 inches long. Now, what we are asking for is, so this is the probability that the sample mean length X bar of 5 fish is between 8 and 12 inches long, right? So here we take a sample of 5 fish, we measure their length, so then we take the mean, the sample mean. This is a sample mean because this X bar, this is the sample mean because we have a sample of 5 fish, right? We have 5 fish. You can measure their length, take the mean, the mean length, and that will be your X bar. The X bar, the mean length of the 5 fish. So what's the probability that the sample mean length of the 5 fish is between 8 and 12 inches long? So this is, so as I said, so remark. So this question is, so here, so this is about the sample mean length X bar of 5 fish. Okay, so it's not the length of a single fish. This is the mean length of 5 fish, right? So it's not. So this is different. So this is different from the length of a single fish. Right? This is of a single fish. Okay. So we have this sample of 5 fish, and you wanna find the probability that the sample mean of the 5 fish, the mean length, of course, of the 5 fish is between 8 and 12. Okay. So again, guys, so this is different from the previous question because in the previous question it was about the length of a single fish. This is the mean length of 5 fish, right? So the question, of course, how do we answer how do we solve such a problem, right? Or how do we answer such a question, right? So how do we solve such problem when where we need to find the probability that a sample mean. So this is a sample mean X bar. A sample mean X bar is between two numbers or less than one number, less than one number, less than some number, or more than one number. more than some number. Okay. Well, so to answer this question, the answer to this question is actually with the central limit theorem. So the central limit theorem. So what does it say, the central limit theorem? Well, actually, there are two versions of this theorem. So we're gonna first, let's use the first version 1. So version 1. So the version 1 is when you have a normal distribution, like in this, like in our example, this length of fish. So version 1. So this is when x. This is for a normal distribution. This is for a normal, when you have a normal distribution. For a normal distribution. So let's say we have x, some random variable. X, this is a variable, random variable with a normal distribution. With a normal, it's normally distributed with normal distribution, and has a mean, population mean. So whose population mean mu is mu, and standard deviation, of course, population standard deviation is sigma. Okay. And then take a sample of size n. So we take a sample of size n. Size n. Okay. And let's say x bar, that's the sample mean. The sample mean. So again, guys, there's difference between this population mean and this sample mean. So like here in our example, like about this the length of fish, this mean mu, this 10.2 inches, that's the average length of all the fish in the lake, all the fish, all the population, right? All the fish in the lake, right? That's the 10.2. That's the average length of all the fish in the lake. Okay, and then like in the question next, the question B, it's about the sample mean x bar of 5 fish. So it's not the mean of all the fish in the lake, but just of 5 fish, right? So there is difference, right, between the population mean and the sample mean. So here we have a sample of 5 fish. So the size of the sample here is 5 because we took 5 fish, right? And we are looking for the mean of the length mean of the 5 fish. Okay, not so the 10.2 represents, that's the average or the mean of all the fish, the length of all the fish in the lake, not just the 5 fish, of course. Okay, so there is difference between the population mean and the sample mean, right? So x bar represents the sample mean. The mu, that's the population mean, the mean or the average of all the individuals in the population, right? Anyway, so this is x.
The mean is the average all the time.
Yeah, the mean is the average. Mean means the average.
Okay.
But like there are like two different kind of average. So this is this population mean and the sample mean. Sample mean is like when you take, as I said, like you have this like the fish in the lake, you take just 5 fish. That's a sample of 5 fish. So when you measure their average, their average length, that's the sample mean. That's the average of the 5 fish. Right, but the population mean, like that's like the average of all the fish in the lake, not just the 5 fish, right? So there is difference.
Okay.
Okay. And So we have this X bar, the sample mean. So then what does it say, this theorem? It says the following. Then this X bar actually follows, then X bar follows a normal distribution with mean, with population mean. So the with so the mean of the distribution of X bar is actually is the same as the mean or the population mean of X is equal to mu. Okay. So the mean of the distribution of X bar is the same as the mean of the distribution of X. Okay. It's the same this mean or population mean of X. So the same mean of X. However, the standard deviation of the distribution of X bar is different. So the standard deviation of deviation of the distribution of X bar, is actually sigma, which is the standard deviation of X over, we need to divide by the square root of the size of the sample. So it's actually sigma over square root of n. So the distribution of X bar, the mean is the same as the mean of X, but the standard deviation is actually sigma over square root of n. So what does it say, this theorem? Like in the concrete examples. So the idea here is that what the theorem says here is that so the distribution of X bar is normal, and so the distribution of this X bar, the sample mean is normal with, so the mean of, so mu of X bar is the same as the mean or the mu of X, okay? And standard deviation of X bar is actually the sigma, the standard deviation of X over square root of n. So when we do a change of variable, so for X bar, so the change of variable, of X bar is actually, so we have your Z would be X bar minus, so it's supposed to be the mean of the distribution of X bar, but the distribution of X bar, the mean of the distribution of X bar is the same as the mean of the distribution of X. So it's X bar minus mu divided by, we're supposed to divide by the standard deviation of the distribution, and the standard deviation of the distribution of X bar is actually sigma over square root of n. So here we are supposed to divide by sigma over square root of n instead of just sigma. So for X bar, it's not just sigma, it's a sigma over square root of n. So for example, let's come back to our example with the fish, right? So we have this example. So let's get back to the example of the fish. So remember, we said this X represents the length of a single fish. This is the length of a single fish, right? And we said X is normally distributed. So X normally distributed, right? And we had our mean, the mean of x. We said it's 10.2 inches. So this is, again, this is a population mean. So this is the average length of all the fish in the lake. Let's say this is population mean. The mean of x, of course. And sigma, the standard deviation of x, is, we said it's 1.4 inches, right? This is the standard deviation of the distribution of x. Standard deviation of x. Standard deviation of x, of course. We're talking about x here. There's no x bar, right? All right, now I have this sample of 5 fish now, right? I have a sample of 5 fish, a sample of 5 fish. Okay. So what's the size of the sample here? Of course, is 5, right? Because I have 5 fish. So n is 5 here. So size of the sample is 5. Right? So n is 5. And I want to find, so there is x bar, right? X bar would be the mean, the sample mean, right? This is the mean of the sample mean. So this is, so x bar, this is the sample mean. So this is the average length of the 5 fish, right? This is the average length of the 5 fish, right? And again, this is different from x. X, that's the length of a single fish. X bar, that's the sample mean. That's the average of the length of the 5 fish, right? Because I have this sample of 5 fish. All right. So now the question was, what's the probability that this sample mean, this average length of the 5 fish, is between 8 and 12 inches, I think, right? We need to find the probability that x bar, probability that x bar is between 8 and 12 inches. 8 and 12 inches, right? So we said, we computed the probability that x is between 8 and 12 inches, right? Like in the first question, the question A, right? Here, find the probability that the single fish is between 8 and 12. So we know how to answer this, right? Using the previous section. Now, we have a different question, right? This is probability that the sample mean, the mean of the 5 fish is between 8 and 12 inches. So we need to find the probability that x bar is between 8 and 12. The sample mean, the average length of the 5 fish, is between 8 and 12. So here we're gonna use our central limit theorem, because what does it say, our central limit theorem? It says, well, this x bar, this is sample mean, this average of the 5, average length of the 5 fish, actually follows a normal distribution. And you can do the same thing as for x, convert x to z, etc., use the chart. But the thing is, for this x bar, well, the mean of the distribution of x bar is the same as the distribution of x, which is mu, but the standard deviation is different. It's the sigma over square root of n, right? So when you convert x bar to z, like the first step, so step 1, like as we did for x, right? We're supposed to convert x to z. Well, here we don't have x, we have x bar, the sample mean, right? So we are supposed to convert x bar to z this time, the sample mean. So to z, of course, to the values of z. So we have, here's your z, right? So, okay. Now we need to convert this 8. This 8 is not the value of x. This is a value of x bar. So we need to convert this value of x bar to z. And the way to do that is, so we take 8 minus the mean. So the mean of x bar distribution is the same as the mean of the x distribution, so which is 10.2, right? 10.2 inches. However, when we divide, so here we're supposed to divide by the standard deviation of the distribution of x bar, not the distribution of x, right? Because our variable here is x bar. Now, what we are saying with our theorem is that the standard deviation of the distribution of x bar is actually, it's not sigma, it's actually sigma over square root of n. Okay, so we need to divide by the square root of n, which is the n, of course, that's the size of the sample, right? We have 5 fish. So that would be a square root of, square root of 5. So here we divide by, here in the bottom, it's supposed to be in the denominator, supposed to be 1.4 over square root of n. 1.4, that's the standard deviation of x over square root of n, the size of the sample, so square root of 5. Right, so again, guys, compared to, to the answer of the first question for x, like here for x, you see, where is it? You see here for x, when you convert the value 8 to a value of z, we subtract the 10.2, and then divide by 1.4. Now for x bar, you subtract the same thing, the 10.2, but when you divide, you don't divide by 1.4, you divide by 1.4 over square root of the size of the sample. So square root of 5 in our example. All right, so here it's a square root of 1.4 over square root of 5. Same thing here for 12. It's 12 minus the same thing, the same mean, 10.2, but divided by 1.4 over square root of 5. Okay, so that's what this central limit theorem says. All right. So here, guys, just be careful because there is like a subtraction in the top, and there is like a division in the denominator. So first, do the subtraction, do the division in the denominator, and then divide. Okay, so what I'm saying here is that, so 8 minus 10.2, of course, that's negative. We know that this is actually negative 2.2, right, in the top. And in the denominator, you are supposed to divide 1.4 by the square root of 5. Okay, so actually that's 0.63. So here it's 0.63. Again, guys, I got this. This is 0.63. That's 1.4 divided by square root of square root of 5, right? Square root of 5 is let me just see here my notes. Square root of 5 is 2.23, right? I think 2.23. Okay, this is, so again, this is 1.4 over square root of 5. Okay, that's how I got this 0.63. All right, then there's z, then there's 12 minus 10.2. So that's 1.8 in the top, and in the denominator, that's 1.4 over square root of 5. So that's, again, that's 0.63. And now I can divide. So of course, here you're gonna get different values than the previous example, right? Because here we divided, you see here, I divide my negative 2.2 by 0.63. And when in the answer of A, the math of a single variable, a single fish, I divided by, of course, negative 2.2 by 1.4, just 1.4, right? So here, of course, we're gonna have a different numbers. So this would be, see, so it's negative 2.2 over, where is it? 0.63, so it's negative 3.49, I think. And then you have your z, and then 1.8 over 0.63, that's 2.86. Okay. And then so once you compute everything, then we can, of course, step 2, where we are supposed to use the chart. And again, this is because z between two numbers, between z between two numbers. So so that will be the area to the left of the second number. So probably that z is less than the second number, the 2.86, minus probability that z is less than the first one. All right, and then we can use our chart as usual. So 2.86. That's so nearest 10th would be 2.8. Nearest 100th would be the 0.06. So in the table that would be 0.9979. Right, minus now negative 3.49. So nearest 10th, it's negative 3.4. Nearest 100th, it's 9 or 0.9. So of course, if you check, let me check the table here, right here, negative 3.4, right? That will be the first, the first row below z, negative 3.4. And nearest 100th, it's 0.09. So that'll be the last number in that row, right? So that's 0.0002. Right, so here, oops. So it's 0.000. I think 3 zeros. Yes, 3 zeros. 2. So that's 0.9977. In other words, multiply by 100. That's 99.77%. So what we are saying is, so if you take a sample of 5 fish, so in other words, if you take a sample of 5 fish, right, then the average or the sample mean, then the sample mean or the average length of the 5 fish, the probability that the average length of the 5 fish between 8 and 12 inches is actually 99.77%. Again, X bar is just the average length, right? So the probability that the average length of the 5 fish between 8 and 12 inches is actually 99.77%. Any question, guys? You see the difference between so there is your variable X and there is this variable X bar, which is the sample mean, right? So, all right, so let's do more examples. And before the second version of the theorem. So the second version, so this first version, this is when the variable X follows a normal distribution. So you may ask, what happens if X doesn't follow the normal distribution? So that's that's actually the version 2 of the theorem. So well, I can state the version 2, or we can do more examples first using this version 1. Let's do more examples. All right. I think we can even do some problems from the textbook. So let's do exercise, for example, 14, page 344. So it says the following. So the heights of 18-year-old men are approximately normally distributed. So the heights of 18-year-old men are normally distributed, approximately normally distributed. With mean, population mean, Population mean. So when I say population mean, I mean you take all 18-year-old men and you measure their length, or their, sorry, you measure their height, right? And then the mean, the average of the whole population, of the 18-year-old men is actually 68 inches. So here it says 68 inches. And with the population standard deviation equal to 3 inches. Standard deviation is 3 inches. Of course, what will be the variable x here, guys? And you guess what's the variable x? What's the variable x? So here, we are talking about the heights of 18-year-old men, right? So the variable x just represents the height of an 18-year-old man, right? That's your variable x, because that's what you're interested in, right? So x, of course, here is just the height. That's the height of an 18-year-old man. Anyway, so we have two questions, A and B. So in A, it says, what's the probability that an 18-year-old man selected at random is between 67 and 69 inches tall? So what's the probability that an 18-year-old man selected at random, etc., is between between 67 and 69, I think. Yeah, 69 inches tall. So here, guys, it's about the probability that a single, just one, right? A 18-year-old man, just one person, right? Just one person here, right? That's only one person here. Okay, now in B it says, if a random sample of 9 18-year-old men is selected. So if you take a sample of 9 18-year-old men, so if a random sample, you take a random sample of 9 18-year-old men, a random sample of 9 18-year-old men is selected. Sorry, this man here is selected at random, of course. Well, it's a random sample, of course. Selected. What's the probability that? So what's the probability that the mean height, the sample mean height? So this is the sample mean height. Right? We have this sample of 9, right? 9 people, right? Or 9 18-year-old men. So what's the average height? What's the probability that the average height, x bar, so the sample mean height, x bar, is between 67 and 69 inches. Right. So as you can see, there is a huge difference between A and B. So in A and B, between A and B, sorry. So in A, you select just one 18-year-old man, right? A single 18-year-old man, right? In B, you have this sample, random sample of 9. You take 9 18-year-old men, and you want to find the probability that the average the average height of the nine 18-year-old men is between 67 and 69, right? So there's a difference between the huge difference between A and B. A and B you have like just one person, one 18-year-old man, and in B you have this sample of nine 18-year-old men, right? All right, guys. Give you a couple of minutes to think about this. So this is very similar to my my example, the example we had with the length of a fish. But anyway, so I'm gonna give you a couple of minutes to think about this. Well, I have the answers. I mean, if you wanna check if your answers are correct. So the answers are supposed to be, so for A, it's supposed to be 2586. So that's 25.86% in B, in A, sorry. And in B, that's there's a huge difference, right, in the answers. It's 0.6826. So which is of course 68.26%. Am I recording? I'm sorry, I forgot. So we're gonna check. Yeah, yes, okay, cool.
I'm gonna go on tutoring today.
Okay. Actually, I'm gonna post a new homework probably on Thursday. So we're gonna have time, of course, to do the next homework because, as I said, next week is gonna be the spring break. So there are no classes, guys, from April 15th to April 22nd, right? So yeah.
Are you professor? When you post it on Thursday, can you post it when you post the homework 6 on Thursday, would it be possible if you could post it early on Thursday so I can go in the tutor room Thursday and Friday? Because I doubt you're gonna be open, right?
No, it's gonna be. You mean like during the spring break? Yeah, it's gonna be open. Well, but I will do my best to post like in the morning, around probably 9 or 10 a.m. I will do my best, but yeah.
Are
I
they
think that,
open, professor, during the spring break, or they're off too, right?
no, they are open. There's no reason to that they close during the spring break. I don't think they. And actually, I'm not sure. I'm sorry.
Because I know I'm utilizing them.
I'm not sure. I need to ask. But
That's the only reason why I asked for Thursday.
yeah,
so
no,
that way
that's
I
a
can
good
have Thursday and
question.
Friday.
Actually, that's a good question. I will let you know tomorrow. I will ask and let you know tomorrow.
Okay.
I don't see any reason why they would close on during the spring break, because I know a lot of people. I mean, a lot of students, they would review during the spring break. So I don't know. I will let you know tomorrow.
Oh, well, you know what? I'm going on there today, so I can ask them.
Oh yeah. Okay. Cool.
That's true. I forgot.
Um, um, So yeah, so after this central limit theorem, next section, I think we're gonna discuss again binomial distribution. The number of successes, etc. So remember, guys, like from the binomial distribution in the table, the values of n. So I think the largest value of n in the table was like 20, right? So you may ask what they are supposed to do if your number of trials n is larger than 20, right? So in the next section, we'll see how to use the normal distribution to find the binomial distribution for n for number of trials very large. So it's like if your n is number of trials is larger than 20, then actually you can use we'll see next section how we'll use the normal distribution to answer such a question. Instead of using the table number 2, we can use this normal distribution. Anyway, I'm just saying that this normal distribution is kind of very important. So as you can see, it measures the distribution of the sample mean x bar. You can also use it for the binomial distribution, etc. Yeah. Oh, all right. Did anyone get the first answer, the 2586? That should be the answer because it's the answer in the textbook. So I guess that it's the right answer. Let me see the chat. Um, all right, guys. I mean, because we don't have much time, so and I want to at least state the version 2 of this theorem. So let's go over A and B together. So for A, it says, of course, so you have your variable x. Your variable x is normally distributed. So you have a normal distribution. You have your population mean, the mu, and which is 68 inches. So that's like the average height of all the 18-year-old men. And your standard deviation sigma is 3 inches. So the question, of course, is to find the probability that a single, just one 18-year-old man is between 67 and 69 inches tall. So you take just one 18-year-old man, so that's your x, and you want your x to be, so you want to find the probability that x is between, probability that x, that's the height of an 18-year-old man, is between 67 and 69 inches. Between these two numbers. All right, so again, this is just from the section. This is a section 7.3, so we know how to answer this. Well, hopefully you know how to answer this. So we are, as a step one, we're supposed to convert x to z. Z. So that will be probability that, so here instead of x, you're gonna have z. Now we convert the 67. That's a value of x to a value of z, so 67. And the way to convert x to z is to subtract the mean. The mean is of x is, where is it? 68, right? So that's minus 68 over sigma, the standard deviation, right, of your x. It's given, of course. It says here 3 inches, so over 3. Same thing for 69. It's minus 68 over 3. So that's the probability that. So here's your z in the top, 67 minus 68. That's negative 1 over 3. The other side, it's positive 1 over 3. So this is negative 0.33 z, z, and 1 over positive. So that's positive 0.33, right? So once you are done with the computations, now we can use the chart. But first, there's a problem here because this is not z less than a number. This is z between two numbers. Between two numbers. So that's between two numbers. So that's the areas to the left of the difference between the areas to the left of the two numbers. So that's probability that z is less than the second number, the area to the left of the second number, minus the area to the left of the first number. So yeah, so once you have this difference, you can use the chart, positive 0.33. Let's do it together here. This is the chart. So nearest 10th, that will be 0.3, and nearest 100th, it's 3, so 0.03. So the answer is 6293. So here it's sorry. So here it's 6293. 93, sorry. Minus, now this is negative, nearest 10th it's negative 0.3, nearest 100th it's 3.03. So we need to go to negative now, negative z, so negative 0.3, so all the way down to negative 0.3. And then we need to go to 0.03, so that's 3707. 3707, sorry. Oops. It's here, 3707. So minus 3707. And the answer, as we said, so it's going to be 0.2586. Right? So in other words, that's 25.86%. All right, guys. So that's for A. For B, any questions so far? Please let me know. I mean, so for B, so we select this random sample of 9. You take a sample of 9 18-year-old men, right? And then you wanna measure the average height of these 9 18-year-old men, right? So in B, it's a different question. So in B, we have a sample of 9. Sample of 9 18-year-old men. So this man, sorry, and the mean. So the n, of course, the size of the sample is n is 9, right? Because it's a sample of That's the size of the sample. Size of sample. Now X bar. So what's X bar? X bar, that's the average of the sample, the sample average, right? Or sample mean. This is the sample average or sample mean. So this is the average height of the 9 18-year-old men, right? So the question is, what's the probability that X bar, the sample mean, the average height of the 9 18-year-old men is between 67 and 69, right? So what's the probability that X bar, the average mean, the average height of the 9 18-year-old men is between 67 and 69. So the variable here, it's X bar. All right, so our using our theorem. So first, of course, as a first step, convert. Step 1, we're supposed to convert X bar to Z, right? Because we're talking about sample mean, not just the one person, but the mean of 9 18-year-old men. So this is probability that, so convert X bar to Z. Now we're gonna convert this value of X bar, which is 67, to a value of Z. So that's 67 minus, so we're gonna use the sample, this is the same population mean, which is 68. But here we're gonna divide by, instead of, you know, the standard deviation of the distribution, which is 3 inches, right? So here we need to divide by 3 over, it's 3 over square root of the size of the sample. So we have 9 18-year-old men. So 3 divided by square root of 9. Okay. The other side is the same thing. So it's 69, right? Take 69 here, minus 68 over this 3 over square root of 9. Right? Again, this is sigma over square root of n. And this is, of course, just the mean, population mean. So that'll be equal to probability that, so your Z, so left side we have 67 minus 68, that's negative 1 over 3 over square root of 9, right? 3 over square root of 9, square root of 9 is 3 because 3 times 3 is 9, right? So 3 over 3, and this is because 3 times 3 is 9. So square root of 9 is 3. Right, square root of 9 is 3, so this is just 3 over 3. So that would be 1. Right, so here we need to divide by 1. That's just 1. Okay. Again, this is just this one here. This is a sigma over square root of n. The other side, that's positive 1. 69 minus 68 over the same thing, 3 over square root of 9. Again, it's 3 over 3, that would be positive 1. So that's probability that Z is between, so negative 1 over positive 1, that would be negative 1, and positive 1 over positive 1, it's just positive. All right, so in other words, this is probability that Z is between negative 1.00 and positive 1.00. All right, so then we can use our table 3. So again, because this is Z between 2 numbers, so that will be Z, probability that Z is less than the second number, 1, minus probability that Z is less than the first number, negative 1. So now I can use our chart. For 1.00, the answer, so positive 1. Positive 1.0. So we go down to 1.0. That's 0.8413. Nearest hundredth is 0. So 8413. So this is 84.8413 minus, this is now negative 1. So negative 1.0 negative 1.0, you go all the way down here. Next to negative 1.0, there's 0.1587, and that's exactly what we want because nearest hundredth is just 0, so 0.1587. 0.1587. This is 0.1587, right? And the difference is exactly the answer, which is 0.6826. In other words, that's 68%, 0.26. Right, guys. Any question? There are no questions, and that's not. I guess it's not a good sign.
Well,
Anyway,
Professor, I have to figure out how to. I have to practice on converting X to Z, so that's why
the
I
X to
have
Z.
questions.
Yeah, the X to Z. It's not. There's actually one. The formula we are using to convert X to Z is just you do like X minus mu over sigma. That's all we do here.
Okay.
Like you see, right here, you start with the 67 because it says like X between 67 and 69. You take your 67, you subtract the mu, the mean, right? The mu is it's given right here. The mu, it's the 68, and then you're supposed to divide by the sigma. That's the standard deviation, so that's 3. So we subtracted the 68, and then we divide by 3. So the idea is always to subtract this population mean mu and divide by this standard deviation sigma.
Oh, okay.
Okay. Anyway, so the homework you can probably, if you practice with the homework, you'll see it's not really hard.
Yeah, I'm
I
gonna
don't think it's
practice
hard.
today. Because remember, I was behind from the probability before.
Yeah.
So I was so
chapter
behind
6.
that. Yeah.
Yeah.
Okay.
All right. So we can do one more example. Well, before the next example, I'm gonna stay the second version of the theorem because, as I said, so if X doesn't follow a normal distribution, so what can we say about this X bar, right? So that's the second version of this central limit theorem. So version 2. So this is when X. So this is version 2 of the central limit theorem, of course. Version 2 of central limit theorem. So this is for any probability distribution. It doesn't have to be a normal distribution. So this is for any normal. For any probability distribution. It doesn't have to be a normal distribution actually. So for any probability distribution. Okay. So in the first version, let me just compare again. So in the first version of this central limit theorem, version 1, we said when X follows a normal distribution, right? We said this is for a normal distribution when X follows a normal distribution. So in this version 2, your X, it's a random variable of, random probability distribution. It doesn't have to be a normal distribution. Okay. Yeah. So what does it say in the theorem? Well, it's almost the same thing. It's just the size of the sample, there are like a restriction on the size of the sample. So suppose, if X has any probability distribution, so of course, for the normal distribution, that will be version 1. Normal distribution. In case of a normal distribution, that will be version 1. Normal distribution, that will be version 1, right? Version 1. So if X has any normal probability distribution, not necessarily normal distribution, with a mean, with a mean population mean mu, with population mean mu and standard deviation sigma. Okay, then the sample mean, X bar, okay, based on a random sample of size n. So here we have restriction on the size of the random sample. It has to be, well, let's say by convention, we agree that, let's say this n has to be of size n larger than 30. Okay. So we need a sample of size at least 30. Okay. If it's not larger than 30, then you cannot really apply this theorem. Okay. So yeah, so then we have the same actually conclusions. So then the sample mean X bar based on this random sample of size n larger than 30 has approach a normal distribution. Approach is a normal distribution. Normal distribution with mean mu. So it's the same mean again. So when you convert X bar to Z, you're gonna use the same mean, and standard deviation standard deviation sigma is sigma over again square root of n. So it's the same formula, right? To convert the sigma over square root of n. Okay, so it's exactly the same thing, except that here when your x's doesn't follow a normal distribution, we require that the size of the sample is more than 30. Okay, 30. So here it's the same thing as version 1. So so what we keep in mind. So here, if X doesn't follow if X doesn't follow a normal distribution, then we can still apply the same formula, but again, you need the size of the sample to be more than 30. We can convert X bar to Z using mu and sigma over square root of n. But the thing is, here we need n to be, we need the size of the sample to be more than 30, and to be more than 30. Okay. So we only have this restriction on the size of the sample compared to a normal distribution. Like, like in this problem with like for the fish or the heights of the 18-year-old men, right? I have this sample. So we have this random sample of 9, right? 9 18-year-old men. So the size of the sample here was 9. That's less than 30, of course. But the thing is, my X follows, in this example, my variable X, it says it's normally distributed. So X follows normal distribution here. So it doesn't matter if the size of the sample is less than 30. That's not a problem. But the thing is, if your variable x is not normally distributed, then you can only apply the theorem. You can only apply the theorem when your size of the sample is more than 30. Okay. So here it's okay because x is a normally distributed. The height of the 18-year-old man is normally distributed, right? That's the same thing for the length of the length of the fish, right? Because we have a sample of 5 fish. Where is it? It's here, right? Where is it? No, sorry. Yeah, here we have a sample of 5 fish, right? That size of the sample here is 5. That's less than 30, but 30. But this is not a problem here because your variable x, the length of a single fish, actually follows a normal distribution, right? We said, where is it? Here, the variable x here in this example. Sorry, where is it? Right here in the top, I guess. Yeah, right here. X follows the normal distribution. So even if we take like a sample of 5 fish, that's not a problem. We can always convert our x bar to z, etc. Right? But yeah, so with this second version of the theorem, all we are saying is if your x is not following a normal distribution, then we need a sample of size more than 30. Okay, 30. All right, guys. I guess I'm gonna stop here. So I can probably tomorrow do an example where x doesn't follow, doesn't follow normal distribution, but the size of the sample is more than 30. So we can apply this second version of the central limit theorem. Okay, and then we can probably move to we can do 1 or 2 more examples, and then we can probably move to the next section. All right. Thank you for listening, everyone, and hopefully I'm gonna see you tomorrow. Thank you all.
Bye.
All right, thank you.
Bye-bye.